Hello chemists, welcome to lecture 9A. Let's first start by discussing something called line spectra. Spectrum is a band of colors made when radiation will separate into component wavelengths with colors associated with each of those wavelengths. Now, in terms of the types of spectra, you should know continuous and line spectra. Continuous spectra are spectra with a continuous range of colors at all wavelengths without any blank spots, so it looks something like this, where there's a continuous range of colors. On the other hand, a line spectrum is a spectrum with radiation that is emitted at specific wavelengths, so the colors are very discrete at specific wavelengths. And that results from an excited gas that has electrons transitioning down from higher to lower energy states, and thereby releasing energy with specific wavelengths and therefore specific associated colors in the process. Now, you should note that different elements will emit lines at different wavelengths and characteristic colors that are used to identify the element. So no two elements will emit the same lines with the same wavelengths or the same characteristic colors. They will always look different. To drive this point home, just take the example of neon versus hydrogen. If you look at neon and hydrogen, they have different wavelengths and different, therefore, characteristic colors associated with them, and that allows neon to be distinguished from hydrogen, or neon to be identified differently from hydrogen. All right, to further drive that point home, look at the isotopes hydrogen 2 and hydrogen 3. Even though they are different forms of the element hydrogen, since they're both the same element hydrogen, they will still have the same exact spectrum with colors emitted at the same wavelengths of 410 nanometers here, 433.9 nanometers here, 486.0 nanometers here, and 656.1 nanometers here. And that's because they're both hydrogens, so they have the same emission spectrum. Even though they may differ in the number of neutrons and their mass number since they're isotopes, they still will have the same emission spectrum because they're still the same element. Same element, still have the same emission spectrum. All right, next let's review the Bohr model from 1913. Bohr's planetary model stated, let's remember, that electrons travel in fixed circular pathways called orbits that look like this around the nucleus, which is held in place by a singular proton in this nucleus right here. And speaking of which, let's remember that a limitation of Bohr's model was that his model only applied to a one electron atom, which was hydrogen. All right, we should also remember that orbits are at fixed distances from the nucleus. So n equals 1 is at a fixed distance, and n equals 2 is at a fixed distance, and so on and so forth. We should also remember that each orbit has a quantized or set and discrete amount of energy at specific energy levels. So n equals 1 has a specific amount of energy, n equals 2 has a specific set amount of quantized energy, and so on and so forth. Finally, we should note that orbits have a maximum number of electrons that each can hold, which we'll discover on the next slide, so take note of that. Let's remember that orbits are also going to be referred to as electron shells or energy levels, each designated with an integer. So just take note of that vernacular. So the first orbit electron shell or energy level is n equals 1. The second orbit electron shell or energy levels n equals 2, and so on and so forth. Finally, we should note that when comparing electron shells, that no matter where the electrons are, they will always have the same charge of -1 because that's just the charge of one electron at all levels. But the difference is that electrons in higher electron shells will have more energy and will be greater distances from the nucleus. All right, because the further away they are from the nucleus, obviously the greater distances they are, and the more energy they have, the higher the n value goes. So for example, for electrons in the third shell, or n equals 3, those electrons will have the same charge as electrons in the second shell, n equals 2, because they're all still electrons, each with the charge of -1. The difference is, however, because electrons in the third shell have a higher integer, electrons in the third shell will have more energy than electrons in the second shell will, by virtue of the fact that the integer is higher, leading to more energy and greater distance from the nucleus. Next, let's go over the maximum number of electrons you can find in each orbit, electron shell, or energy level, which is 2n squared. All right, so make sure you note that. Where n equals the integer representing the electron shell energy level or orbit. So for the first energy level, electron shell, or orbit in a neutral atom, which is n equals 1, you have 2 times 1 squared, or 2 electrons maximum. In the second electron shell or energy level of a neutral atom, you have n equals 2 for that, so you know that the maximum number of electrons that can hold is 2 times 2 squared, or 8 electrons. The third level, n equals 3, you plug in 2 times 3 squared, maximum that can be held in the third shell is 18. And the fourth shell or energy level, n equals 4, so you know the maximum electrons that can hold is 2 times 4 squared, or 32 electrons. Now, in terms of how we actually place these electrons within these orbits, according to the Bohr model, what you have to do is you have to place electrons as closely to the nucleus as possible when filling the orbits. because that is associated with something called the ground state configuration, which is a configuration where electrons are in the lowest electron configuration possible in terms of energy. Speaking of how we arrange the atoms or configure electrons, let's talk about the two types of electron configurations associated with the Bohr model: the Bohr ground state electron configuration and the Bohr excited state electron configuration. Now, the Bohr ground state electron configuration for an atom represents the lowest possible energy configuration of electrons in each electron shell because you place the electrons in the lowest possible energy levels. Where you can find the Bohr ground state electron configuration is if you open up to your periodic table in your reference tables, you'll find that they're represented by the lower left set of numbers with dashes on the periodic table. So, for example, if you look at calcium and you look at the lower set of numbers separated by dashes, you'll find that for a neutral calcium atom, the ground state electron configuration for a calcium atom is 2-8-8-2. All right, so this Bohr ground state electron configuration is also known as like kind of a ground state shell configuration, 2-8-8-2. Now, how do we interpret this configuration? Well, we have to read the numbers from left to right. The first number reading from left to right in this configuration represents the number of electrons in the first shell. The second number reading from left to right represents the number of electrons in the second shell, and so on and so forth. So reading from left to right here, for a neutral calcium atom, reading from left to right here, since the first number reading from left to right here is 2, we know that there are 2 electrons in the first principal energy level or electron shell of a calcium atom. In the second principal energy level or electron shell of a calcium atom like this, based on this configuration, since the second number is 2, we know that there are 8 electrons. Reading from left to right, the third number reading from left to right is 8, so we know the number of electrons in the third principal energy level or electron shell of a calcium atom is 8. And finally, the fourth and final numbering from left to right in the shell configuration is 2. So we know that the number of electrons in the fourth principal energy level or electron shell of a calcium atom is 2. All right, that's how you read this. That's it. All right, in terms of finding the number of protons, all you have to do is only when you have a neutral atom can you add up the number of electrons in the ground state configuration and set that equal to the number of protons, because we know that's true for electrical neutrality in a neutral atom. If we add up the 2 plus 8 plus 8 plus 2 here, we know that there are 20 electrons as well as 20 protons in this neutral calcium atom. Now, the next type of electron configuration, an excited state electron configuration, is a higher energy configuration for electrons than the ground state configuration. And that's usually due to one or more electrons being promoted to a higher electron shell. How do you identify excited state configurations? Just find any configuration with the same number of electrons as a neutral atom of the element, but that does not match what's found on the periodic table. So if we look at a calcium, for example, we know that in a neutral calcium atom that the number of electrons will equal the number of protons and therefore the atomic number, because that's what defines an electrical neutrality. Since we have 20 protons in a neutral calcium atom, we can also presume there are 20 electrons in a neutral calcium atom. So based on that fact, if we compare that to this, we know 2873 is an excited state configuration for a neutral calcium atom. Why? Because it has the same number of electrons as a neutral calcium atom, which is 20, but it does not match the configuration of 2882 found in the periodic table. So therefore, 2873 is an excited state configuration for calcium. Why is that? If you think about it, we took one of the electrons from the third principal energy level, or electron shell, and promoted it to the fourth electron shell, thereby making it 2873 for an excited state configuration of calcium as opposed to 2882. All right. Next, let's discuss valence electrons. These are electrons in the outermost shell or energy level of an atom. This is also called the valence shell of an atom. Now, to find the number of valence electrons, all I have to do is look at the number of electrons in the outermost or final shell. So basically look at the final number in the configuration, and this will give you the number of valence electrons. So let's look at the Bohr ground state configuration for silicon, which is 284. Since the last number in this configuration is 4, we know that silicon will have 4 valence electrons because, again, 4 represents the number of electrons in the outermost or final shell of a neutral atom of silicon. Boron obviously has 3 valence electrons, so 3 is the number of electrons in the outermost shell of a boron atom. Now let's discuss how to convert between ground and excited state configurations. Note here that I have explanations for what happens during these conversions, as well as how to write each type of configuration. You should note that the explanation is really what you should write on any standardized exam, while the writing configuration part is not to be written on an exam. It simply helps you to acquire the skills you need. All right, so let's go into this. First, when you convert ground to excited state, energy is absorbed to promote one or more electrons to a higher energy state, producing dark line or absorption spectra down here like this, with these dark lines representing wavelengths of radiation absorbed. Now, to write excited state configurations from ground state configurations, just promote one or more electrons from a lower to a higher energy state without violating 2n squared and while keeping the number of electrons the same. You can just do this by subtracting one electron from a lower shell and adding one electron to a higher shell to represent an electron transitioning to a higher energy state. For example, to write an electron configuration for a zinc atom in an excited state, all you have to do is take its ground state configuration of 2, 8, 18, 2 from the periodic table, subtract 1 from this third shell, giving you 18 minus 1, or 17 in the third shell now, and add that one electron to the fourth shell, giving you 2 plus 1, or 3 in the fourth shell now. And this new configuration of 2-8-17-3 represents an excited state configuration for a zinc atom, where one electron was promoted from the third to the fourth shell. Next, when you convert excited to ground state configurations, energy is emitted with specific wavelengths as one or more electrons demote to a lower energy state, thereby producing bright line spectra or emission spectra down here like this, with the specific colors corresponding to specific wavelengths of light that are emitted. Now, to write ground state configurations from excited state configurations, it's very simple. Just add up the number of electrons in the excited configuration, then use that number to match it up to the atomic number and number of protons of an element on the periodic table. And this is, of course, presuming you have a neutral atom. Then you just have to find the associated ground state configuration. For example, for the excited state configuration 2682, to find its ground state configuration, just add up 2 plus 6 plus 8 plus 2, giving you 18 electrons in this atom. And this matches an atomic number of 18 and 18 protons. So presuming this is a neutral atom, that represents argon. And if you look up argon's ground state configuration in the periodic table, that's 2-8-8. So there's your answer there. Okay? Next, let's discuss how emission spectra are produced, which involves multiple steps. First, absorption happens where an electron in a lower energy state gains or absorbs a specific amount of energy as heat, light, or electricity, moving to a higher energy state further from the nucleus called the excited state. For example, an electron in n equals 1, a lower state, absorbs energy and moves to n equals 3 in excited state. After absorption, emission occurs. During emission, an electron in a higher excited energy state returns to a lower energy state, emitting or releasing a specific amount of energy as light with specific wavelengths and colors, where the emission spectra specific wavelengths and associated colors are used to identify the element. For example, an electron in n equals 3 in excited state will release a specific amount of energy and return to n equals 1, a lower state. Note that defining emission spectra on a standardized exam will help explain how to produce fireworks, bright line spectra, and flame colors, so note that for your homework and for future exams, such as the Regents and the SAT Chem. Last, let's discuss how to interpret bright line spectra and to identify elements in a mixture. Step 1, find wavelengths of spectral lines in the mixture so you have wavelengths in the mixture to compare to those of known elements. Step 2, compare spectral wavelengths of lines in known elements to those in the mixture to see which elements match. If all spectral wavelengths of an element's lines are found in the mixture spectrum, then the element's definitely part of the mixture. Basically, you need a complete match for an element to be part of the mixture. For example, for element D down here to be in the mixture, all 6 of these lines must match the lines in the mixture spectrum down here. Alright, by the way, the second step explains how bright line spectra help identify metal ions and salts on exams, so note it, please. Now, let's try this first example. In this first example here, the mixture spectrum down here is spectral lines at 10 different wavelengths between 750 and 360 nanometers with very few increments. So it's hard to tell where a spectral line's wavelength lies between 360 and 750. Luckily, you can match up elements' lines to lines in the mixture as if you were using a ruler by just drawing lines down from the element spectra, since all these spectra happen to be the same size. Okay? So let's try this out. So for element D, first of all, to be in the mixture, all 6 of its lines must match lines in the mixture. So let's check. If you draw lines down from element D for all 6 of its lines, what you'll find is they all align with lines in the mixture spectrum, meaning spectral wavelengths of all 6 of element D's lines are found in the mixture, and hence element D is definitely part of the mixture. All right, now apply the same principle to element E. If you do that, all 4 of element E's lines must match lines in the mixture, and if you draw lines down from element E for all 4 lines, they all align with lines in the mixture spectrum, meaning Spectral wavelengths of all four lines in element E are found in the mixture, and hence element E is also part of this mixture. All right? Yeah. If you apply the same idea to element G, you'll find that element G is not a complete match. Not even the first line, in fact, of element G matches up to anything in the mixture spectrum. So element G is not part of the mixture. Only elements D and E are part of the mixture, since they're the only two elements where all of their line spectral wavelengths are found somewhere in the mixture spectrum. Okay? Now let's try the second example on the right here. Note as you go from left to right on this spectrum that the wavelengths decrease. If you use the scale down here, you'll find that the mixture has lines with spectral wavelengths at 743 for the first line, which is closer to 750 than it is to 700. 740 for the second line here, which is slightly lower in number. Let's say 35 for the third line, which is closer to 750 than 700, but is still further down in terms of number. 710 for this fourth line, which is closer to 700 than it is to 750. 675 for the fifth line, which is between 700 and 650. And 610 here for the sixth line, which is closer to 600. Now I want you to take a minute with the scale down here to approximate wavelengths for the spectral lines in elements A, B, C, and D. Okay? If you do that for element A, you see spectral lines have wavelengths of 707 here, 650 here approximately, and 640 here. None of which match up to the mixture, so element A is definitely not in the mixture. For element B, however, element B's spectral lines have wavelengths of 743 for this first line, since it's closer to 750, and 675 for the second line, smack dab in the middle between 700 and 650. Both of which are found in the mixture, so element B is definitely part of the mixture. For element C spectral lines have wavelengths of 740 for this first line, which is very close to 750, 735 for the second line, which is close to 750 but lower in terms of number than the first line was, 710 for this third line, which is even closer to 700 than the second line was, and 610 this fourth line, which is closest to 600 nanometers out of these four lines. So since all four of these lines match up to lines in this unknown sample, element C is also in the mixture. Element D, if you approximate the spectral line's wavelengths, fall around 725 for the first line here, 715 for the second line, let's say 65 for the third line, 635, let's say, for the fourth line, and 610 for the fifth line. Even though the last line at 610 here is found in the mixture, because only one spectral line's wavelength of element D is found in the mixture, element D is not in the mixture because it's not a complete match. So element D is not in the mixture. Hence, we conclude that only elements B and C are in the mixture, since all of element B's spectral line's wavelengths and all of element C's spectral line wavelengths are found in the mixture. All right, that's it for today. Please make sure you complete these notes for tomorrow's class, and make sure you do the problem set at some point. Thanks. Bye-bye.